Hello everyone, in this video I'm going to talk about logistic regression, which is one of the most popular and widely used learning algorithms today. And specifically we're going to discuss the classification problem where the target variable y that we want to predict is discrete value or having a discrete value. So here are some examples of the classification problems that we have made mention in the previous video. Like we talked about email spam classification as one of the classification problems that we have cited. And another example is classifying online transactions. So say for example, if you have a website transactions and you might be interested to know whether it's fraudulent or not. Say there is some cases of stealing credit cards or stolen passwords, etc. So we also have another example as classifying tumor as malignant or benign or non-malignant. In this problem, the target variable y that we are trying to predict is having two values, 0 and 1, and that is, for example, whether it's spam or not spam, fraudulent or not fraudulent, or malignant or non-malignant. So another name of 0 here is a negative class, that means benign tumor, and another name for 1 is a positive class that is classified as malignant tumor. Say for now, we'd like to look at the classification problem having two values here, as we have mentioned, two possible values of our variable y, and so we call it as binary class problem that has either a value of 0, 1, or yes or no, or true or false. But we also have actually another type of classification problem having more than two values, and in this case we call it multi-class problem that can either have a value of 1, 2, 3, or 4. So how do we create a classification algorithm? An example of a training set for a classification task, say, where we intend to classify tumor either it's malignant or benign, and if we notice our target variable y here, the malignancy will only take a value 0 and 1. So perhaps looking at this, we might think of creating a model based on the algorithm that one we have already discussed. If you haven't checked the previous video, please check out linear regression video that we have uploaded. And say we apply the linear regression to this data set and fit a straight line or regression line to it, given the y of x, which is b sub 0 plus b1x plus the error value that is looking for the slope of the line as well as the y-intercept. And so we can come up with this regression line. And by the way, we can actually refer this to as our hypothesis function, h theta of x, where we get the regression line or the best fit line. And if we want to make prediction, one thing we could do is to threshold the classifier output y of x or h theta of x at 0.5, that is at the vertical axis value y, our target variable, we have 0.5 here. And if the hypothesis outputs a value that is equal to or greater than 0.5, we predict y is equal to 1. Otherwise, we predict y is equal to 0. That is lesser than our threshold, that is 0.5. So using this threshold, 0.5, and using or utilizing the regression line over here like this, here, we ended up classifying everything at the right side of this here as positive class or malignant, while everything at the left of this line here or this point will be classified or predicted as negative class. So in this case, it seems that the linear regression is doing well, even though this is a classification task. But say, for example, let's try changing the training samples a bit, and say we add another data, like extending the samples a bit. Let's say somewhere here, we have another training sample over here. And if you look at this, there seems to be no changes at all, because it will basically follow the ones we mentioned earlier here, which means that if the tumor size is greater than this value here at the 50% threshold, then y is equal to 1. we classify this as equal to 1, as you can see here in this line. Okay? However, otherwise, if it's a small, or if it has a smaller value, then it is classified as 0 or non-malignant or just a benign over here. So, however, once we added one training example here, and if we run linear regression again to create a best fit line, then it might look like this. As you can see here, it has another line of regression, and if you look at again the threshold that we have set, for example, 0.5 as we have done earlier, so we ended up having that or having something like this. So everything at the right side, or all points at the right side, it will be classified as positive, and the data here are predicted as malignant, and the data at the left side will be predicted as negative. And as you can see here, it seems pretty bad thing for this linear regression because as you can see, these are our positive examples, and these guys over here are our negative examples, which basically separates the samples right here, and here. But by adding another training sample way right here, this would be classified as malignant. However, somehow this sample here caused the line of hypothesis to change, and thus have caused to give us quite not good hypothesis, as these guys here will be classified as non-malignant. See here? So applying linear regression to classification problem is most of the time or often not a great idea or not a good idea, as we have seen in this illustration. And another thing, worst thing here as we move to the next slide, is that using linear regression in classification can somehow also result to something unpredictable results. For classification, we know that y is equal to 0 or y is equal to 1. But if we use linear regression where the hypothesis can output value that is much greater than 1 or even much lesser than 0, even if the training samples are labeled 1 or 0. So it might be possible that if you train data sets that are labeled by 0 or 1, still it can give us a hypothesis value y, or a predicted value y, that can be way greater than 1 or even lesser than 0. So in logistic regression, we see to it that our function, logistic function, or a sigmoid function right here, will actually give us values from 0 to 1. That is giving us the probability that a certain new data point or instance will be classified either 0 or 1 depending on the threshold that we have used. Okay, that's all for the logistic regression as applied in classification problem. And in the next video, we are going to discuss further logistic regression in the function or the sigmoid function that's being used, as well as the use case that we can cite. Thank you, and see you in the next video.